talk a little bit more about dipole-dipole forces, and then we will move on to hydrogen bonding and wrap up our discussion about intermolecular forces. And also, we will have a preview of coming attractions when it comes to mixing of substances, and then we're done. Okay, so that's it. Talking about dipole-dipole forces, hydrogen bonding forces, and then mixing, and then that's it. So before we get into chemistry, what questions, concerns, comments do we have? Anything? Okay. If that is the case, I'll give you 1 minute in your groups to complete the question on the screen, and then we'll move on. So this is just to remind us about dispersion forces, and then we can move on to something else. Go ahead. Yes.
Yes.
Were you able to complete the exam?
No, no.
Why not?
Hey, when did you reopen that?
Okay.
Oh, it's not Gmail, it's my
Outlook.
yeah. Because I got one
I think submissions are open. The
Can
question.
you open
Yeah.
that? Thank you so much.
I got the one for today.
Now, can you search for 151?
Oh, maybe it's. No, yeah, no. I bought my.
No, this is.
Done. Yeah. And then for my lab session. But I don't think it's good way.
Yeah, every Friday we have a quiz. Don't forget that next day.
Yeah.
But if you come to my office, suppose tomorrow, I'll give you a deal.
Okay,
Yeah,
okay,
deal.
deal.
So I actually reopened that and sent out an email to everybody who missed the quiz. I don't know why you didn't get it.
I did not get that. I didn't get that either.
Oh, you missed that too?
Yeah, you know, I didn't get it.
I got his email, but I can't remember yours. But I remember
I
his.
did the same thing with that day.
You missed it too?
Yeah.
What's going on with you now?
Dude,
Yeah, I got
dude.
I was a referee.
It was a yeah.
It was bad.
Everybody, let's have a office hour party tomorrow. Yeah, we'll have a 8:30. Just
8:30?
for like 5 minutes.
Wait,
AM? Is it too early in the morning?
No, I just I don't know.
Oh, you can come at 9 o'clock. 9, yeah, 9 will be fine. Just for 5 minutes.
Okay.
All right, that should be enough. Oh, it's too loud. I like this stuff. All right, discussion will be closed in 5 seconds, so please submit your answers. We are close to 90%. 1 more second. All right. All right. So please pay attention. I still feel like people are talking about a few other things now. I really want you to pay attention. I only have 75 minutes with you. I want that 75 minutes. Okay. You can, if you want more time to talk with your friends, arrange that later. I want that 75 minutes now with me. Okay. All right. All right. So now, I'm sorry. I didn't mean to scare you. I'm sorry. Okay. Anyway, let's see what went on here. So here are our answers. The most popular response is this. HF has the weakest dispersion forces, and HI has the strongest. Now, why this is the correct answer as well? Let's see how many of us got there. Okay, this needs to be better. Only 62%. Okay. Anyway, so I don't know. Maybe some of you swap this order, but I can live with that as long as you understand what's going on here. Now, can somebody explain what's going on? Why is this the order? Joel, thank you for volunteering. Why? Why this is the dispersion force strength order?
I did it. I looked at the periodic table and I looked
Okay.
at the molar mass and just ranked them based off of like the bigger we got, the strongest dispersion forces. I don't know if you can always use that, but that's what I put.
We never use that.
Oh, never use
Never
that.
use that. Okay.
Okay. Well,
Now, what do we use though? We organize our notes. Joel, in our notes, what did we write the other day? Okay, and so dispersion forces depends on what? Can we check your notes? See if I can do that too. I'll check mine, you check yours, okay? So we wrote, okay, I need to expand this. Joel, do you have this in your notes? This.
I meant.
Okay, perfect. Yeah, that means you're right. That's absolutely correct. Okay. So all right. Again, I think you'll mention the same thing. So dispersion force strength depends on the polarizability, which depends on the number of electrons and the size. Okay. So when it comes to these molecules, HF has the lowest number of electrons. Okay. So if you count the electrons, let me see. I can count. I knew how to count a long time ago. Let me see. Okay, so hydrogen brings us 1 electron, and then fluorine brings us 9. Therefore, HF has 10 electrons. HCl has 18. HBr has 36, and so forth. Okay, so you can say that we have the least number of electrons in HF. Therefore, that is the least polarizable, meaning it has the weakest dispersion forces. On the other hand, HI has the greatest number of electrons, therefore it is the most polarizable. Okay, therefore it's going to have the strongest dispersion forces. You will have questions like this on your test. I'm talking about exam 3B now. Okay, so you will have questions like this. But do we have any questions, concerns, comments about this? It's really simple. All right, but you need to be focused now. Okay, so you count the electrons. The species with the most number of electrons is most polarizable. That is the train of thought. Okay. Most number of electrons means most polarizable. Most polarizable means strongest dispersion forces. That is it. Done. Yeah? Any questions, concerns, comments at this point? I'm really trying to emphasize this. By the way, dispersion forces is the weirdest intermolecular force. I mean, the weirdest type of intermolecular forces out of the 3. Once we get through that, everything else is downhill. It's much, much easy. Okay. So I really want you to make sure that you understand it. If you do not, if you have any confusion, please ask. That's all I'm asking you to do. When I give you problems like this, I want you to struggle. I really want you to struggle. Okay. The reason is that's how so you're struggling means you're challenging yourself. And if you challenge yourself, that's when you grow. Okay. So, and then if you do not do that, then, if everything is easy, and then you can you understand everything I say, there's no growth at all. Why? You already know what I'm talking about. So what's the point? Right. But if you will be learning something new, if I challenge you, so that's what I'm trying to do here. Okay. So anyway, so there are 3 possible structures, like I mentioned in the question itself. And then if I drew the line structures for those, I would draw like this. So we have 1, 2, 3, 4, 5. This will be 1. 1, 2, 3, 4, 5. This would be another one. And this would be another one. So 1, 2, 3, 4, 5. Okay. This would be the 3 structures possible. Now, what questions, concerns, comments do we have about this? Yes, sir. Thank you. Carlos, love questions. No, not me. I'll love answering them. I'm sorry.
I just wanted to ask about like 2 that I had drawn and if they would also
I
work.
want.
Yeah.
Yeah. So okay, I have a question about a structure. Okay. So now please pay attention. Okay. You might have the same thing as well. So if you do a structure like this, 1, 2, 3, 4, 5. Okay. What's the problem with this? Remember, our molecular formula is C5H12. Okay. Now, if I convert this to a Lewis structure so that I can count my carbons and hydrogens, my bens are carbon atoms 1, 2, 3, 4, 5, and the common bonding pattern is fulfilled by carbon hydrogen bonds. Okay. I will be adding only 10 hydrogen atoms. So the problem with this structure is what? You destroy 2 hydrogens. We cannot do that. Yeah? Any other questions, concerns, comments at this point? Any other questions, concerns, comments? All right, now, so we know we're still we are in the process of talking about intermolecular forces, but this is just kind of a detour in a way. Okay, but here's the real question behind this. I'm gonna call this A, B, and C. Okay, here's the question. Which structure, which molecule do you expect to have a higher, the highest boiling point? A, B, or C? Go ahead. Which molecule or which substance out of A, B, and C do you expect to have the highest boiling point? Person responses no. Meaning I'm going to close this question in 5, 4, 3, 2, and 1. Still. Okay. And here are our responses. Okay. Okay. So yeah, this is good. Okay. So these are options. And then we selected our options. Okay. But one of them is correct. Okay. Which one is it? Okay, that's democracy. I mean, but it has, so science has nothing to do with that. Okay. Just because the option C is the most popular answer, it doesn't make it correct. Okay, that's all I wanted to say. I'm sorry. We don't have to bring politics here. All right. Now, let me do it this way. I'll show you the actual boiling points. Okay. Here are our structures. Okay, so here's the structure A, and here's structure B, and here's structure C. Okay, so if somebody wants to, have the same one as we drew before, here's 1, 2, 3, 4, 5. Here's 1, 2, 3, and 1 going up. Here's 1, 2, 3, and 1 going up and down, or something like that. Okay, so something like this. These are the A, B, and C. Okay, now here are the boiling points. All right, 30 seconds. What's going on here? How do we explain this? Hi, how are you? All right. Who's going to tell me why? What's going on here? How do we explain this? So according to the boiling points, I want you to pay attention now, okay? According to the boiling points, which one has the strongest intermolecular forces? Which one? A, B, or C? Hey, thank you, A. All right. So now, why that is the case? By the way, are these molecules polar or non-polar? They're non-polar, okay? They're made of only like hydrogen and carbon. Hydrocarbons are non-polar for all intents and purposes, but that's a different point. Now, here's what's going on here, okay? I wrote this model, right? So I'm going to model the B, molecule B here, okay? So here's what we have in B. Unfortunately, I don't have 2 of these. I only have 1. So this is my B, okay? So, but A would be
I don't know. Let's see. A would be something like this. This is my A, okay, linear molecule. But when it comes to B, you have an umbrella sticking out. Oh, that reminds me of umbrellas, my grandmother's umbrellas. I'm serious. All right, I'll tell you that story a little bit later, okay? Anyway, so it is like this. Now, what does this do? So, I mean, I told you like this. I mean, this reminds me of my grandma's umbrella. Okay. So when she went out, doesn't matter what the weather is. It can be like really beautiful outside. Like, okay, she would always carry not one but two umbrellas. Okay. And I asked her why. Okay. She said the umbrellas are not to protect her from the sun or rain or something like that. It is to act as a barrier between her and other people. Okay. I mean, this was extremely relevant during the COVID era. Yeah. So these umbrellas sticking out, I'm not umbrellas, I'm sorry. Let's call them branches. Okay. These things that are sticking out act as barriers for the molecules to come closer to each other. If you cannot come closer, guess what? You cannot have strong interactions. Yeah. If you want to have strong interactions, you must be able to get closer. Otherwise, it doesn't matter like, how many electrons or how strong intermolecular forces you can have. Okay, if there are not things or umbrellas preventing you from getting closer to each other, then you cannot have strong interaction. Okay, so that's why in B and C you have weaker intermolecular forces, okay, or in this case weaker dispersion forces. They are for lower boiling points. And in A, because you have more surface area of contact, because you don't have this branching or umbrella sticking out, the molecules can get closer to each other. And as a result of that, you're going to have a higher surface area of contact between A molecules compared to B and C. And that's why you have strong intermolecular forces and higher boiling point in A compared to B and C. Yeah? All right. Can you make a small note in your own words, like, whatever you understand? And you can check with your friends as well at your table to make sure that we are on the same page. Go ahead. But there's something.
Right. So it's really important that you write what you understood in your own words. But just as a clutch, okay, I wrote something on the slide as well. The larger the area of interactions or larger the surface area of contact, the stronger the intermolecular forces. Okay? It is not just relevant to dispersion forces, okay? It is relevant to any intermolecular forces. Okay? It doesn't matter whether you have the strongest intermolecular forces in the universe, okay? If you have branches sticking out that act as barriers for the molecules to come closer to each other, then you're not going to have stronger interactions. Okay? So branching or these things sticking out like my grandmother's umbrellas act as barriers for the molecules to get closer. Therefore, it reduces the surface area of contact. Okay? That's why intermolecular forces are weaker in B and C. Any questions, concerns, comments at this point? Okay. Surface area of contact or interaction points. I think I saw interaction points in your exam, I think, maybe. Anyway, so play a key role when it comes to any type of intermolecular forces. Okay. So let's try to explain this. By the way, while you're doing this, I'm going to say things, that's all I do, right? It's say stuff. Okay. So your exam 3B will include material up to Unit 3, Module 2. Okay. Now, knowing that next Tuesday is a holiday, we won't be meeting on Tuesday. So we will have to cover some content on Thursday, a little bit. But I'll still review on Thursday. But here's what I'm going to be doing. I am going to be posting a video, a lecture video, an entire lecture video on Unit 3, Module 2, the polymers. Okay, so that you can, you can watch that. You can make your own notes before Thursday, so that you will be super prepared when it comes to Thursday. Okay, so I hope that you will make use of that. Now I'm going to send out tons of emails reminding about the same. Okay. Each activity has a take-home message, right? The previous one, we talked about how branching, affects the surface area of contact. How the umbrellas of my grandma affects the surface area of contact. Okay, that was the point in the previous one. Okay, now this one also has something like that too, right? So let's figure that out. I'm going to close this question in 5, 4, 3, 2, and 1. Okay. By the way, everything that you need to think, all the tools that we need to think about this problem is already Okay, we have already covered all that things. Okay, so you will see when I talk about this. Let's see your responses. Okay, most of us selected these, which is great. So I'm going to go over them one by one. So most of us selected A, or benzene intermolecular forces are stronger. That is absolutely correct. How do we know that? We see we have a higher boiling point for benzene. Therefore, it should have strong intermolecular forces. Now, if this did not come naturally to you, please remember that in a previous life, it seems like a previous life, okay? So we wrote something like this in our notes, just to remind us that they are in our notes, okay? The stronger the intermolecular forces, higher the boiling point, melting point, density, viscosity, all those good stuff, but lower the wave pressure and lower the volatility, okay? So this is just connecting to that, okay? That first point. So that is correct. Now, moving on to point B, dipole forces. Why are we talking about dipole forces here? Yeah, are these molecules polar or non-polar? Non-polar. If they're non-polar, do we have dipoles? No. If they don't have dipoles, guess what? There are no dipole-dipole interactions. Okay, so there's no reason why we would even entertain option B beyond dipole-dipole. I did not even read the rest. Okay, so there are no dipole-dipole forces in these molecules. Why? These are non-polar molecules. One more time, just to remind us, last week we talked about how if your molecule contains only hydrogen and carbon, in other words, hydrocarbons are non-polar for all government purposes, and that this boils down to that. Okay, option B. Yes, this is government work. All right. Anyway, option C. Benzene is more polarizable as it has more electrons. Okay, this is good. Not most of us selected that. Now we see that we have more atoms in hexane. So we are getting 6 times 6 electrons from carbon, and then 12 times 1 electrons from hydrogens, meaning we have 48. 48 electrons in hexane. But benzene has only 6 times 6 from carbon and 6 times 1 from hydrogen, meaning we only have 42 electrons in benzene. So electrons wise, benzene has less electrons, making it less polarizable compared to hexane. Okay, so that's why most of you did not select option C, where it says benzene is more polarizable. In actuality, benzene is less polarizable than hexane. Option D, benzene has a greater surface area of contact. That is wonderfully correct. Okay. Now, why that is the case? If you think about the atoms in benzene, okay, you have 1, 2, 3 electron domains around them, meaning we have what electron domain geometry? If you have 3 electron domain geometry is Thank you, trigonoplanar. And because all of these are bonding electron domains, what about the molecular geometry? It's also trigonoplanar, meaning all these carbon atoms are planar. Yeah, so if you have planar carbon atoms in our molecule, all of these are planar, then what you have in your hand is something like this, right? So this is a plane, and this is another plane. These are two molecules. Guess what? They can stack on top of each other like this, increasing the surface area of contact. Yeah, planar molecules have a higher surface area of contact, okay, because they are planar, right? Because they can stack on top of each other like this, okay? And that reminds me of a food. What is that? Pancakes. And that's why students who wrote pancakes in the previous exam got points, even in the pre-response. That's okay. I mean, that helps us remember things, like, yeah. So anyway, so therefore, option E is correct as well. That truly reminds me of pancakes. All right, I'll reopen this. And then I'll take any questions you might have. By the way, I want to say one more thing about hexane. Even though I don't have a hexane in my hand, a model of hexane in my hand, I have pentane. Pent means 5, hex means 6. I only have 5. I only could find 5 carbon atoms. Okay, so anyway, so this is my pentane, and hexane looks similar to this. Okay, so compared to benzene, look at this. This is not planar, right? On top of that, these molecules, these bonds are single bonds. They rotate all the time, like this. Okay, they rotate all the time. As a result of that, it decreases the surface area even more compared to something like benzene, because of these rotations, making them, not maintain the linear geometry, linear structure. Okay, so that's why benzene has a higher boiling point, because it has a greater surface area, like a rigid, greater surface area of contact, which is going to increase, the intermolecular force strength vastly. Yeah. All right. What questions, concerns, comments do we have at this moment? Anything? Any questions that I can clarify? Try to clarify. I can only try. Anything? Yeah. All right. That looks beautiful. Okay. Some of us really want, like 5 of us, okay, really wants to stick with the dipole story. I don't know why. We're gonna stick to our guns. No matter what Pereira says, I don't care. Right? Okay, that's okay. Okay. All right. Now, with that, I'll move on. We'll move on to something like this. Now, I'll give you a hint. The hint is we are done with the surface area concept. Okay. Having a greater surface area of contact increases the intermolecular force strength. Right. That point is, we have driven that home already. Okay. We're done with that. We're moving on. Now, that is my hint. So, you don't have to bring in the surface area of contact to explain this. Go ahead.
Yeah, I think this one.
Oh, this is nice.
This one is a big part.
Okay. All right. So the good thing about something like this is you have a 50% chance of getting it right, right? Yeah, this is a gambling question. I hear you. So, all right, let's think about this. Oh, by the way, when I first came up with this question, AI wasn't popular. Okay, maybe like 20 before 2020, I believe. Okay, anyway, that's why I use Google. I mean, you can still use Google, but anyway. So let's think about this, right? By the way, this isomer has a special name. Can you remember? Who remembers that? This isomer on the left, what do we call that? Remember we named them? We did this. Can you remember? No? Okay. So, all right. I really hope that we did that. Otherwise, I'm going to be embarrassing myself. Oh, here you go. See? Remember we did this? We drew them? What do we call this isomer? Yeah, it's called the trans isomer. All right, that's enough. Okay, let's move. No, I mean, move enough from the book. Okay, all right. So we have the trans isomer, and then we have the cis isomer over here. Okay, so the difference here is, let me see your answers. You know what? Let's not see your answers. Okay, I mean, I'll see them later. All right, so the dipole moments of the trans isomer cancels out because they are equal in magnitude, but opposite in direction. They cancel each other out. Therefore, this is a non-polar molecule. Non-polar. Okay. On the other hand, this is isomer has two dipole moments going to the chlorines like this, the bond dipole moments. Therefore, the net dipole moment must be going to, let me use the thickest pencil possible. Okay. Net dipole moment must be going like this. So this is polar. Okay. So both of these have the same number of atoms, same number and types of atoms. So as a result of that, we can say that the dispersion forces, let me call this, sorry. I want this and the pencil. Okay. So this is my trans isomer and this is my cis isomer. They both have comparable dispersion forces. Why? The number of electrons and the size of the molecule are like, are comparable, right? So therefore, dispersion force strength is kind of, comparable as well. However, in the cis isomer, because it's a polar molecule, there's something else going on. Does anybody know? If it's a polar molecule, that means it has a permanent dipole. If your molecule has a permanent dipole, what else do we find in the polar isomer then? What else do we have? I cannot hear, I hear that, but I didn't hear from everybody. So if your molecule is polar, we have what other intermolecular forces? Everybody. Thank you. Dipole forces. So this is on top of dispersion forces. Okay. So therefore, when I include the dipole contribution here, you see that you have overall stronger intermolecular forces in the cis isomer, and therefore we can expect that to have higher boiling point, melting point, density, viscosity, but lower volatility and lower vapor pressure. Yeah, that's the idea there. All right. What questions, concerns, comments do we have at this moment? Now, the point is this. The dipole contribution of the polar molecules is on top of dispersion forces. Everything has dispersion forces because everything has electrons, meaning everything is polarizable. Okay, so therefore everything has dispersion forces. But on top of dispersion forces, if your molecule is polar, you have dipole forces as well. And that's why overall intermolecular forces are stronger in the cis isomer or the polar isomer. Joel.
I wish that you were silent like this for me as well. Why so again, okay. Go ahead.
I was just gonna say, if like we had a question like this on like a free response or something, what would be like
That's fun, right?
the most efficient way to explain like why the second one has a higher boiling point? Just like in a simple,
Bar chart like that?
yeah.
Yeah, that will nail it. Yes.
Okay.
Yeah. I mean, if you draw a bar chart like that, and then maybe write a small. So bar chart tells me that you know what's going on, that
Right.
you deserve all the credit for me.
What would
I mean,
you
know,
write
just
if
to
you were
make sure
writing
the
that?
TAs understand it too, you can say the polar isomer has dipole contribution on top of dispersion. Therefore, therefore it has strong intermolecular forces. That's it.
Okay.
Yeah. Yeah. All right. Any other questions, concerns, comments? All right. So that is about that is revisiting I mean, I like revisiting things, especially in unit 3, module 1, because that reminds us about things. Yeah. So again, just the dipole forces only occurs if your molecule is polar. If your molecule is not polar, then there are no dipole forces. And then we also wrote that in our notes as well over here. Okay. I'm just making the connections. Okay. For dipole forces, you need to have a polar molecule because it depends on the molecular polarity. All right. Now with that, let's have some more fun. Here we go. When I walk around, I feel like, we're kind of, I don't know, I mean, how to put this nicely. Addicts. Is that a real word? Like, we are addicted to our phone. This is worse than cocaine, as far as I'm concerned, Yeah. I mean, not just you, even me. Okay. So when I'm in the class, it is easier for me for some reason because I'm having so much fun walking around, talking, and I'm seeing what you're doing, being nosy. Okay. I mean, I don't have to be addicted to my phone, at least when I'm in the class. But when I'm at my office, like at my desk, I know I want to say it. Okay. But I mean, I see that here as well. But anyway, so I want you to be cognizant about that. That's going to act as a barrier for you to be your best possible version. Okay, so that's an addiction. Okay, your phone is an addiction. But if you think about and if you're cognizant about it, you might be able to control that and be better at not being at it and being better at performing at your best. I'm inviting you to do that. Okay. All right. Anyway, I'm sorry. I mean, I had to bring it up. I don't know why. All right. Anyway, so here's the most popular order. And this is the correct answer as well. How many of you flipped this? Can you see the hands? How many of you flipped this? Okay. You should put away your phone. I'm sorry. All right. I was kidding. Okay. No, anyway. So please, if you flip this, that's okay. As long as you understand what's going on. Okay. So HF has the strongest dipole forces. Why? It is the most polar molecule. And how do we know it's the most polar molecule? Remember, the dipole moment is proportional to delta chi, the electronegativity difference. So for HF, it is 2.1 minus 4, the absolute value is 1.9, right? Something like that. Anyway, for HCl, it is 2.1 minus 3.0, the absolute value is 0.9. For HBr, H is 2.1, Br is, I believe, 2.7 or something like that. Therefore, the absolute value is 0.6. So you have the greatest electronegativity difference in HF, therefore that is the most polar molecule, therefore that is going to have the strongest dipole forces. And that's how we know that this is our correct answer. Yeah? All right. What questions, concerns, comments do we have at this moment? Yes, Joel. Carlos, I'm sorry, I need you. We should keep like a mic stand near Joel.
Oh my God, no.
I was kidding.
this dipole forces, is it always dependent? Activity? Like,
Difference,
you
yeah.
just look at the periodic table and decide?
Yeah. I mean, it's a linear molecule. I mean, that's the only way to do it.
Okay.
Yeah. I mean, even if you draw the vectors, I'll do it. It's fine. Okay. So HF would have the longest dipole moment, highest magnitude, and this would be HCl, and HBr would be the smallest dipole moment vector. That's another way to visualize it. Any other questions, concerns, comments? And one more time. Again, this is the reminder. Stronger the dipole moment, or more polar the molecule, stronger the dipole forces. That is the take-home message here, and that is what we have in our notes at the beginning as well. And when we said the dipole forces depends on the molecular polarity. Same idea. Any questions, concerns, comments at this moment? Anything? Any questions at this moment? Right? If that is the case, I'm going to clear my. Yes, sir.
Will we get the electronegativity table in the exam?
All right. Yes. And I already given that to you. I already posted the front page of the exam on your D2L site. Please check. That's all the information you have in front of you during the exam. So, I think that has electronegativity table. Yeah. Please use that when you do your quizzes, homework questions, so that you get used to, what we have during the exam, and then what is not. Okay. All right. So with that, let's do this. Now, for this question, I'm okay with you using AI or Google, or I don't know, Gemini, Copilot, ChatGPT. What else do we have there? Claude, or whatever you want to use. Okay. Can you find the boiling points and then arrange them, and then and justify them as well? So you can use your chemistry knowledge to justify it, but you can use like AI to cheat. Okay. So maybe if you want to, you can predict your boiling points and then check, use the AI to check whether your prediction is correct without just moving on to AI directly. It's totally up to you. All right, 30 more seconds. Please submit your answers. All right, I'll give you 10 more seconds. Is there, right? Okay, so we have more than 90% responses now. Therefore, I'm going to close this question in 5, 4, 3, 2, and 1. Right? Yeah. Okay. All right. So, you know what? So I'm not going to think about this for the moment, okay? So let's do it like this. Let's do a bar chart, right? And what do I mean by bar chart? In the bar chart, I have IMF strength on the y-axis, and I have the species, let's say HF, HCl, and HBr on the x-axis is y and x. Okay. So the dispersion of forces depends on polarizability, and we know HF has 10 electrons. We counted them before. HCl has how many electrons? How many electrons does HCl have? How many? Thank you. It's 18. Okay. So if we did not count that, okay, chlorine atomic number is 17. Therefore, it has 17 electrons. Hydrogen atomic number is 1. Therefore, it has 1 electron. Therefore, 17 plus 1 is 18. That's how we got that. And then similarly, HBr has, I think, 36 electrons. Okay. So based on the number of electrons, HF is the least polarizable. Therefore, it's going to have the weakest dispersion forces. And then HCl, right? And HBr has the most number of electrons. Therefore, that's going to be the most polarizable with the strongest dispersion forces. Okay, dispersion forces wise.
Oh.
And then the dipole forces, HF is the most polar molecule. Therefore, you're going to have the strongest dipole forces in HF. Let me call this DD. And DD for dipole. Okay. And then HCl is less polar than HF. Therefore, you're going to have, I don't know, something like this. Oh, maybe this too short. That's okay. Should be something like this. And HBr is the least polar molecule. Therefore, you're going to have the weakest dipole forces in HBr. Okay. So based on this, HBr must have the strongest intermolecular forces, meaning the highest boiling point. And then maybe HF or HCl, maybe let's say HF based on this, and then HCl. But the most popular answer, or after checking your AI, you're telling me that HF has the strongest, and then HBr, and HCl has the weakest. What's going on? What's going on here? How do we explain this? Anybody?
Isaac,
Go ahead.
because we're forgetting about hydrogen bonding.
Okay, yeah. So the only way to explain this is by adding another contribution called hydrogen bonding forces. Okay, so HF on top of dispersion and dipole has another very strong kind of intermolecular forces called hydrogen bonding interactions. We call this HB. Okay, and that's why HF has the highest boiling point, meaning strongest intermolecular forces, and then HBr, and then HCl has the weakest. Okay, therefore it's going to have the lowest boiling point. We just explained that. Okay. So before I take your questions, okay, the take-home message here is there's another type, the third type or the last type of intermolecular forces is known as hydrogen bonding forces. And hydrogen bonding forces, I'm going to come back to this, forces occurs only, let me go back, I'm sorry. Okay, only and when we have hydrogen, I cannot erase that. Okay, here we go. Hydrogen covalently bonded to either nitrogen, oxygen, or fluorine. That's the requirement for hydrogen bonding. if you do not have hydrogen covalently bonded to nitrogen, oxygen, or fluorine, you don't have hydrogen bonding forces. Okay. With that, what questions, concerns, comments do we have at this moment? Any questions, concerns, comments? Joel, anything? No? Okay. Anybody? Taya, how's it going? I haven't heard from you from a while. Okay. In a while. I'm sorry. Any questions, concerns? Do we have a question? Thank you. Yes. Yes. Remember names one more time?
I'm Reese.
Please go ahead.
I thought that like hydrogen bonding forces were like the weakest out of all three, right?
No.
They aren't?
They're usually very, very strong. One of the strongest.
Never mind.
Really?
Yeah.
Yeah. Okay, never mind then. I take my question back.
No. I mean, that's not true. Okay. It is not a biology or chemistry, physics thing. It's a science thing. Okay. Hydrogen bonding forces are pretty strong compared to anything. I mean, the other intermolecular forces. Okay. Usually. So, because we compare the weakest of hydrogen bonding with the weakest of the other ones, you will see the weakest of hydrogen bonding is much, much stronger than the weakest of the other ones. I'll show you that in a minute. Okay. So it doesn't matter whether you're learning biology, chemistry, or physics, or whatever it is. Okay. It has to be the same thing. Okay. So yeah, that's not true. Yeah, so it's read into that, but it's not a biology thing or a chemistry thing. Yeah. Okay. Now, anyway, going back to, I'll reopen that question too in case I'm not. All right. All right. So I'm going to revisit research questions in about 5 minutes. But for now, okay, one more time, just to reiterate, hydrogen bonding, please make sure that you have this clear in your mind. Hydrogen bonding only occurs when you have hydrogen covalently bonded to nitrogen, oxygen, or fluorine. Okay. What is happening in those interactions is our hydrogen atom is going to get sandwiched between two highly electronegative atoms. So in this case, it's fluorine. Okay. So you can see that hydrogen is in the middle. Okay. So, and you can think about this, HF is a highly polar bond. Okay. And then you have this partial positive charge on hydrogen is interacting with the partial negative charge of this, the fluorine, which is highly electronegative. Okay. So that's what's happening here. And there are other examples of hydrogen bonding interactions. Okay. Like this. I want to point out something to you. So you can see that the hydrogen doesn't have to get sandwiched between the same electronegative atom. Okay. For example, in this case, you have a nitrogen over here, and we have hydrogen covalently bonded to that. That's the requirement. And that can get sandwiched between this nitrogen and an oxygen like this. Okay. This is the hydrogen bonding interaction. This is another example. So this hydrogen, which is bonded to oxygen, it is sandwiched between this oxygen and then a fluorine of HF. So that's another example of that. Okay. So just keep that in mind. So these are hydrogen bonding interactions. When you draw hydrogen bonding interactions, by the way, you will have to draw these interactions. Okay. You always have hydrogen covalently bonded to either nitrogen, oxygen, or fluorine, and that hydrogen is interacting with another electronegative atom like nitrogen, oxygen, or fluorine from anywhere else. Okay. And then you use like 3 dots between that hydrogen and oxygen, or the other electronegative atom to indicate the hydrogen bonding interaction. Yeah.
Why doesn't this type of force also include, for example, chlorine, which has the same electronegativity as oxygen?
Okay, your question is so it.
Yeah. Why does hydrogen bonding?
Yeah. So
only have to be
fluorine
these
is a larger atom compared to nitrogen, oxygen, or fluorine. If you think about nitrogen, oxygen, or fluorine, we see a pattern, right? They are in the same period, meaning that they're smaller. So for the hydrogen bonding forces, we only consider those nitrogen, oxygen, fluorine, which are in the same one. Why? They are much smaller. So therefore, you have much
strong interactions, why they can get closer to each other? Yeah? That's a good question. Yeah, I like it. But it's just a name, okay? There might be so I know HCl might interact with in a similar way, but they are not just called hydrogen bonding interactions. They are just dipole forces. So just to summarize, this slide summarizes everything that we have learned so far. Okay, so if you think about any molecule, they have electrons, therefore they are polarizable, therefore they are going to have dispersion forces. But if your molecule is polar, on top of having dispersion forces, you can have dipole forces as well. But if your polar molecule has hydrogen covalently bonded to nitrogen, oxygen, or fluorine, just like these two guys, on top of dispersion and dipole forces, you can have hydrogen bonding forces as well. Okay, so this should help you identify the types of interactions, types of intermolecular forces in any given molecule. And there's a small video on the channel as well that I made like a long time ago as a key to identify any type of intermolecular forces between molecules. If somebody reminds me, I can post that on our day2 site. But it's the same idea in a different way. And then coming back to Risa's question about the intermolecular force strength, for comparison, covalent bond energy ranges from 200 to 1,000. They're very strong. But intermolecular forces ranges from 0.05 to 40 kilojoules per mole. Pretty weak compared to actual covalent bonds, actual bonds. Okay, that's something that you have to keep in mind. Now, within the intermolecular forces, the dispersion forces range from 0.05 to 40, dipole 5 to 40, and hydrogen bonding is 10 to 40. You can see that even dispersion forces can be as strong as dipole or hydrogen bonding because they can go up to 40. However, you might have heard, like Chris mentioned, right? So people know that hydrogen bonding forces are known to be the strongest type of intermolecular forces. The reason is the weakest of the hydrogen bonding force is 10 kilojoule per mole, which is much higher, 2 times greater than the weakest of dipole, and then 20 times greater, I think 20, is it? And something like that. Anyway, compared to the dispersion forces. So that's why hydrogen bonding forces are considered as the strongest type. But keep in mind, if you have enough electrons, the dispersion forces can be stronger than, or as at least as strong as hydrogen bonding or dipole forces. All right, any questions, concerns, comments at this point? All right, so not today, but on Thursday, I'm going to bring some example. I'll bring an activity to show how dispersion forces can outweigh the dipole forces. But for now, we'll live with this. Yeah. Okay. As our last 2 activities for today. Okay, let's try this. Now these are 2 molecules, two different molecules. They interact too. So they are called mixing. So if we have interactions between different molecules, that leads to the idea of mixing. So we are getting into that. So this is the preview of coming attractions when it comes to mixing. So we're talking about between CH3CH2OH and CH3CHO, okay? So between the 2 molecules.
All right, we have close to 90% responses now, I think. Okay. I'm going to close this question in 5, 4, 3, 2, and 1. And this is good. Almost. Okay. So yeah, so between any molecules, you're going to have dispersion forces. That's why most of us selected that. Okay. And then our molecules are polar, both of them are polar. Therefore, they're going to have dipole-dipole interactions. That's right as well. And they can have hydrogen bonding forces as well, because this hydrogen covalently bonded oxygen can interact with the oxygen of this atom, this molecule. Therefore, you can have hydrogen bonding interactions as well. We haven't even talked about ionic bonds. Ionic bonds only occurs in ionic compounds. These are not ionic compounds, so that is out. Covalent bonds are not intermolecular forces. They are intra, or they are within the molecules, not between molecules. Therefore, option E is incorrect. The correct answers are A, B, and C. Okay. I'll reopen that and I'll take questions. Meanwhile, can you draw them out for me, those intermolecular forces? Last question for today. One for the road. For the line structures, that would be the easiest thing to do. So I like drawing the line structures. So let me point that out to you. So CH3, CH2OH. We have 2 carbons, 1, 2, and then the second one is bonded to oxygen and hydrogen like that. And for CH3, CHO, we have 2 carbons again, 1, 2, and the second one has this going on. Okay, so that would be the line structure for the second one. So if I use those, so here's my first one, and then here's my second molecule, and then here's my electron cloud for the first one, and here's my electron cloud for the second one, and then I'm going to assign partial charges randomly, plus, minus, okay, minus, plus, okay. You can have interactions between these opposite partial charges which are induced. Okay, so that's going to be my dispersion forces. Oh, I used to, when it comes to dipole forces, you know what? I start by drawing the dipoles. Let me show you what I mean. You know, dipole forces are always like this, head to tail, here's one dipole, and then here's the other dipole, he's in the tail of the first one. I see this all the time in the dog parks. All right. Anyway, so here's my first. Now I'm going to draw the molecule on top of that. Here's my one of the molecules, and then here's my other molecule on top of that. Voila, done. Dipole forces. Last one. Give me a second, raise. Okay. Hydrogen bonding. So hydrogen bonding is about this hydrogen. It has to be this. That's the only one. And that has to get sandwiched between this oxygen, which is covalently bonded, and the oxygen of the other molecule like this. Okay, so here's the rest of the molecule, and then I would indicate three dotted lines between this oxygen and the hydrogen, and that is my hydrogen bonding interaction. That's it, done. Okay, so by the way, you will have to draw these, not the exact same molecules, like these three interactions in your exam. Okay, so get used to drawing them, visualizing them, and ask questions. Okay, we'll have some more fun when we come back on Thursday. We will start polymers on Thursday. That's my goal. Okay, with that, oh my goodness, it's 12:16. Here's the attendance code for today. Everybody else have more fun on Thursday.